UCSD ECE 111, Lecture 2, Introduction to System Verilog. This is the set 1 where we cover some basics of structural versus behavioral design in Verilog. This is an overview of what we will be covering. There are different ways to specify a piece of hardware. And there are different ways while we specify it, it's going to be used. One way is to use it in simulation, and the other way is to use it in synthesis. In simulation, we will be using model SIM in this class. And this can allow us to do verification of the design. We want to see the functionality. Does it behave as required? And the register level, logic level, and timing can be given to us in model SIM. The synthesis, we use Quartus Prime. In the TA session, we'll be covering these two tools and how you could get your hands started and trying to write your first pieces of code. A Verilog module that we've covered last time in lecture 1 as example has this port and module name, in and out, and the relationship between the input and output. But there are different ways we could write this in a structural Verilog. How we write this function is we write about like the structure, how things are connected. This could be, for example, even the structure of a gate level, but typically when we say structural design, it's a little bit higher level. Or we could have behavioral level, like what we've seen before, when you have a Boolean logic description and we just tell the software, this is what this piece of hardware is intended to do, but we're not going to tell all the details about the design. So we will learn more about this in lecture 4. Let's go through a structural design. In this particular case, this is only a gate level. This is for example purposes. Here we're designing an XOR gate with inputs A and B, output out. But then what we want to do is we want to specify this gate by gate. Here we are composing gates to form a more complex module. We could write an XOR gate as a concatenation of inverters in AND and OR gates, and this is exactly what we are doing here. The inputs are still A and B, and the output is out, but we have these intermediate points that are connecting these modules that we've designed before. In this particular case, the modules are just simple inverters and an OR gates, which is only for demonstration purposes. As we've seen before, Verilog actually has these constructs added in the syntax, so we don't have to specify them like this every time. But the important point to take from this slide is this notion of a wire here. This wire is are the points that are connecting these internal points in the design to each other. For example, the AND gate is connected to T1 and T2, which is basically just the outputs of these AND gates, which are going to the last OR gates, which is implementing this design. This is a structural design that we just saw in the previous slide. In the behavioral design, we just describe output as a function of inputs, like what we've seen before. In XOR case, there is the syntax of Verilog provides XOR for us, so we can just write out is A XOR B. And if you're an experienced designer, this is most likely the path you will take for designing an XOR in a complex system. Now, let's just compare this design for structural behavioral for another example. Let's assume I'm going to design a 4-bit adder in both structural and behavioral design. If I'm doing just a behavioral design, all what I need to do is to just define the functionality of a full adder. In this particular case, Cout is equal to Cin and A added to A added to B, and this is enough as a behavioral description to define this as a behavioral structure. Now in a structural, I could actually write 1-bit full adders and then use them to by concatenation to build a 4-bit adder. And of course here I need the 1-bit adders as submodules, and then I need wires to connect them. Simply put, I have A0, B0, and S0. Here is Cin. This is full adder 1. Then I'm going to connect it to the second, third, and fourth full adder. Then I'm going to get the C out, which is the output I was looking for. And the bits here are S1, S2, S3. And I need to define new variables here, which are basically wires that are making this structural design possible. Let's take a look what it looks like in the computer program. Looking into the description of this module in the behavioral model versus the structural model, which we just draw on the board, what we see here is that we are basically having that one full adder module that is written before, and we are calling that full adder module. Every time we call it, we give it a new name, and this is really essential in understanding the language, because every time we instantiate, we call the module, we are really creating a piece of hardware in the actual design. So this is something that we need to be very careful about, because every time you call a function or you put a variable, we are basically putting a register or a piece of logic in the design. The wires here are basically just connecting those the full adder, 1-bit full adders to each other, and this way we can write this small structural behavior in the Verilog format. Now we will go to the next set where we talk about the basics of the module elements.